Alright, so we're going to be taking a look at Newton's method. So if you're a senior or if you're going to graduate as a major in mathematics, you want to pay attention to this because this is on your oral exam. Okay, so we have some function. Well, that might be kind of weird to, okay, that's fine. We want to try to approximate the location of the roots. And so we start with an initial guess, go up to the curve, and then we draw the tangent line from the curve. And the new point is the new guess. Okay, so let's go through those steps that we just did. Let me get a little space here. So we went from x0 and then we went to f of x0. So this is the point on the graph that the line has gone through. The slope of the tangent line, remember, f prime of x0. Therefore the equation of the tangent line is y minus f of x0 equals f prime of x0 times x minus x0. Good. Now what's the location of x1 here? X1 is where you replace x by x1 and then you replace y with 0. And then you solve this for x1. So if I divide by f prime, right, and then just add the x0 over to the other side, I get that x1 is equal to x0 minus f of x0 divided by f prime of x0. Okay, and then when you get x1, then you just repeat this process until you get xi plus 1 is equal to xi minus f of xi divided by f prime of xi. And that is, and this, you can't really see my eye there, that is Newton's method. Good, so it's very simple to look at and very simple to incorporate. What's really nice is that Newton's method, if you start close enough to where you need to be, Newton's method converges very, very quickly. In fact, we would say it converges quadratically. Now, I should say that some issues can appear. One of them, of course, is that we have the derivative in the denominator. What would happen then? So, for example, at this point, what happens to the tangent line? It is a horizontal line. Does a horizontal line touch the x-axis? No. So therefore we would be in trouble. Okay, so we would want to make sure that the derivative here is not equal to 0. Of course, it might happen that the derivative is 0 at the same spot, that your root is going to be 0. And it's interesting what happens in this kind of a case. In fact, why don't we just see what the iteration procedure would be in that case. Alright, so using f of x equals x squared and f prime of x equals 2x, what would our iteration algorithm look like? It would be xi plus 1 is equal to xi minus x squared, xi squared divided by 2xi. But notice, right, that the xi's cancel. So you have xi minus, what is that, 1/2 xi, and that's 1/2 xi. So what's going to happen is that, right, your intercepts are just coming right in. You know, you're cutting the distance in half at each stage. And so, you know, if you plug in anything and you start repeating this process, right? If I start with an x0 and I take 1/2 x0 and then I take 1/2 times 1/2 x0 and then keep repeating that over and over again, what's going to happen? Yep, x sub 0 is going to go to 0. Now if it's on the negative side, it's kind of interesting. In this case it won't do anything funny, it'll just go to 0 on the negative side. Yeah, and it'll go very fast, right? You're cutting your x coordinate in half each time. Okay, so in fact, though, it only converges linearly instead of quadratically, I guess, huh? All right. So weird things can happen with Newton's method, but it works very well for most functions. Let's see. Before I leave Newton's method, I just wanted to talk about how we actually implement these. Implementing bisection and Newton's method on the computer. So I should say that both, I believe both, Python does have a version. I was going to say MATLAB does not have specialized versions for these. They're so easy to code, though, that we can just do it ourselves. And so we have our own code. For these. Bisection, you only need f of x and the interval, right? What do we need for Newton? I better spell this right. It's looking pretty sloppy there. Newton's method, we need f and f prime. And the initial point, x0. And then we need some, for both of these, we need some kind of tolerance level. Okay, for when the solution is good enough. Okay, because you're never going to get exactly 0, so you're going to want to give your algorithm a little breathing room there. So the purpose of my little tangent here is I want to talk about how do you pass a function or a function name into a function. Right, we know how to define functions in both MATLAB and Python, but now I need to figure out how do I pass a function into a function. And so yeah, one way to do it, let's talk about MATLAB's version first. You can use an anonymous function. I guess we haven't talked much about functions yet, have we? Anonymous function handle. And so in that case, MATLAB has just changed this recently. For example, f is, you use an @ symbol, and then whatever symbol you're going to use for your formula, we'll just use x because that's what everybody uses. And then right after that, I do need parentheses around that. And then you just put in whatever your formula is, like x cubed, I guess in my example, plus x minus 1. Okay, and then similarly, you could write one for the derivative if you wanted to. Well, maybe I'll wait on that for just a sec. So now we can call our bisection algorithm. I think I called it bisection. Well, I didn't. I left off the ION for some reason. Then you just say f. And then in this example, the 0 is bracketed between 0 and 1. And we're going to let the tolerance be 5 times 10 to the minus 5th. And then it'll output the x. Good. And then in Python, the anonymous function handle uses a lambda instead of an @. And so you would say f equals lambda. Be sure to spell that right. X. And then it uses a colon. And then x cubed. They don't use a caret for some reason. I like using a caret. Plus x minus 1. Good. And then the Python function, I think, is bisection. I should have called them the same thing. But the way it passes through is exactly the same. Good. And so again, the bisect.m file is available on our class website, and bisection.py is available on our class website. We're going to actually put these into a larger script file, so we don't have to have a lot of separate functions when we're doing these. But we'll talk about that in the next video. Okay, I should say just briefly that for Newton's method, we need both y and y prime. I'm going to say y and dy, dy over dx. So what I've done is I usually, have my function output two different things. So in MATLAB that would be function, and then I would say like y dy equals function, was it test func 1 x, and then down here you would write y equals whatever, dy equals whatever, and then you'd end your function. In Python you have to do a little bit differently. In Python you would have def and then like test func 1 x, remember the colon, and then you could just write these in your command line if you want. Then you'd have your y equals and your dy equals, but then down here you would have return y comma dy and then it would return both of your outputs. Okay, the problem with this is I'm running over time, but in MATLAB it's kind of nice, because in MATLAB if you only ask if I'm outside of MATLAB, outside of this function now, and I say a is equal to test func 1, and then I put a 3 in, for example, what comes out? Well, if you only have one value here, it just outputs the first value. And so you could use the same function then in bisection. Unfortunately, Python does not do that. If you say a equals test func 1 of 3, in this case it actually outputs an ordered pair with your y and your dy. And so in the code then I've had to separate that out. So change bisection to deal with this. And you'll see that in the code that I've actually had to make a little change. Okay, sorry for going so far over. I'll stop here.